Hello, welcome to lecture number 11 of the course Quantum Mechanics and Molecular Spectroscopy. As usual, we will start with a quick recap of the previous lecture and then proceed with the lecture number 11. In the previous lecture, we talked about the electric field and magnetic fields of the propagating light. So, if a light is propagating along a direction r, or let us say its vector is represented by r, then there is a electric field which is has a direction E, and the corresponding electric field is E, and there is a magnetic field B with the corresponding direction. Okay. Now, there are three components of both electric field and a magnetic field. So, E will consist of Ex, Ey and Ez. Similarly, the magnetic field will have three components, that is Bx, By and Pz. Okay. But in the Hamiltonian we have potential and not the field. So, we need to convert this into potentials. So, there is a transformation that takes the electric and magnetic field to scalar and vector potentials. Phi is the scalar potential and there is a vector potential A which will have three components, Ax, Ay and Az. So, totally we have four components, one scalar potential and three vector potentials. So, four components. And these four components must be reduced from the electric and magnetic fields which have 6 components. And the relationship between the magnetic field or the electric field with the vector and scalar potentials are E is equal to del phi minus dA by dt and B is equal to del cross A. Okay. Now, what we will do is, since we have to go from 6 components to 4 components, of course there is some redundancy. So, there are infinite ways one can have this transformation. One of the transformations that we will call it as Coulomb gauge, in which we say phi is equal to 0 and del dot A equals to 0. So, there are 6 components. So, you are reducing to 4 components with 2 criteria that are fixed. Okay. So, therefore, now the transformations becomes easier. Okay. Now, in a plane wave notation, A is given as A is equal to A naught and it will move in the same direction as the electric field, this one, into e to the power of minus I k dot r minus omega t, sorry this should be plus e to the power of minus I k dot r minus omega t. Okay. Now, this is exponential I theta plus exponential minus I theta. So, this is proportional to cos theta. Okay. And you can see the electric field is a time derivative with respect to vector potential. So, E will be equal to minus I A naught epsilon, or plus I rather, e to the power of minus I k into omega k dot r minus omega t minus e to the power of minus I. So, this should be plus k dot r minus omega t. So, this should be proportional to sin theta. So, which means the vector potential A and the electric field E are out of phase with respect to each other by pi by 2. So, they are out of phase by pi by 2. Okay. Now, let us get on to the contents of this lecture. For example, if you take a charged particle and you put it in the electric field or electromagnetic radiation, that is light, then the charged particle experiences what is known as a Lorentz force. Okay. Okay. This Lorentz force is experienced by charged particle in electromagnetic field. Or this electromagnetic field is nothing but light. So, if I expose a charged particle to the light, then it feels a Lorentz force. So, I will write Lorentz force as Fl. This is equal to Q times electric field plus V into B, okay, where you know this is electric field and B is magnetic field, V is the velocity of the particle. Okay. So, of course, that will depend on the charge Q. Okay. So, more the charge, more will be the force. For atomic systems, of course, atomic and molecular system, the charge is fixed because the electrons have fixed charge. Okay. Of course, nuclei could have a different charge which could be multiples of the electronic charge E. Now, this is the force that is called Lorentz force. But let us take a small detour and think what is force in terms of classical mechanics. Force in classical mechanics. Okay, what is force as classical? Force F equals to mass into acceleration. Okay, so this is mass and this is acceleration. Okay. Now, acceleration is nothing but rate of change of velocity. So, this is nothing but F is equal to m times dv by dt. That is nothing but rate of change of velocity. Okay. Now, mass is a fixed quantity, it is a number for a given particle. So, one can write F is equal to d by dt of mv. Okay. Now, what is mv? Momentum. This is nothing but momentum. Okay. So, now force can be written as d by dt of mv, that is nothing but d by dt of p. So, force can also be reconciled as rate of change of momentum. So, this is nothing but rate of change of momentum. Okay. Now let us get to the Lorentz force. Okay. Fl is equal to Q times E plus V times P. Now in general the magnetic field, its magnitude is going to be much smaller, okay. So one can neglect, okay, and if you neglect that, we get Fl is equal to QE, okay. This is called electric dipole approximation. Wherein you are only looking at the electric part, electric field of the electromagnetic radiation, okay. So we are neglecting the magnetic field. Of course, if you are going to do spectroscopy like NMR or EPR, this is not, it's not going to be valid, but for general spectroscopy terms like rotational, vibrational and electronic, this is valid, okay. Now Fl is equal to Q dot E, okay. Now I can write this as Q times minus d by dt of A, okay, because E is equal to del phi minus dA by dt. That is what we said in the Coulomb gauge you have d phi is equal to 0. So which means E will turn out to be minus dA by dt. Now if I write this, your Fl is equal to, of course Q is a charge of a system, so that can be taken out, it is a constant with respect to time, okay. So this can be written as minus d by dt of QA, okay. Now but force is, this is force, okay, Lorentz force is given by d by dt of minus QA, okay. Now force, as I said, is equal to d by dt of P, that is nothing but rate of change of momentum. Okay. Now if you compare these two forces, of course force is a force, whether it is of some mechanical origin or of electromagnetic origin, it is a force that is required. Okay, now you can clearly see by comparing these two equations, you can see momentum P is equal to minus QA. Okay. This is the momentum that a charged particle will gain in a vector potential, okay. So in your Hamiltonian H, okay, what you have? You have P square by 2m plus your potential V of x, okay. Now but P in this case is the velocity or the momentum that a particle has on its own. But the momentum you put, the moment you put the charged particle in the electric field, then its momentum is going to get modified. So your P prime will be equal to P plus, okay, the newly attained momentum because of the electric field, P of the, because of the electric field. And that is the perturbation that you have. So your P prime will now be equal to P minus QA. So your Hamiltonian H will be nothing but, actually it should be P prime square by 2m plus Vx. Okay. Now let us write the in terms of, okay, this is not really the so your Hamiltonian, so you write the corresponding operators. So this will be equal to P minus QA square by 2m plus V of x. Why V of x? Because I told you that for this course, okay, the potential is generally independent of time. Okay. So this is equal to H into, now this will be nothing but, what is your P? This is nothing but minus IH bar d by dx, that is the P, minus QA whole square by 2m plus V of x. That is my Hamiltonian. So when I write that, so your Hamiltonian H is equal to minus IH bar d by dx minus, I am only looking in the one dimension case, okay, one can generalize to 3 dimensions, okay, minus QA whole square P square by 2m plus V of x. So this is nothing but a square plus b square plus 2ab. So a square will be minus h bar square by 2m d square by dx square, a square, that is b square will be q square a square by 2m, okay, but 2ab, okay, or it cannot be 2ab because they are operator ab minus pa, okay. In fact, I can take a negative sign outside, so this is equal to ab, this is minus and this is minus, so just ab, so h bar plus h bar by h bar by 2m h bar by 2 I h bar by 2m, okay, d by dx of QA plus, okay, and if I multiply this, this will be QA times IH bar by 2m QA times d by dx, okay, this whole times potential V of x, okay. So your H will now be equal to minus h bar square by 2m d square by dx square okay, minus h bar d square. So this is q square by a square, this will be plus IH bar by 2m, let us say, d by dx of QA plus IH bar by 2m QA d by dx plus q square a square by 2m plus V of x. Now we will see this equation, if you take the first term and the last term, this is nothing is normal Hamiltonian. So H is equal to minus h bar square by 2m d square by dx square plus V of x plus IH bar by 2m d by dx of QA minus plus IH bar by 2m QA d by dx plus q square a square by 2m. Now this is nothing but your H naught, the Hamiltonian of the original molecule. So your H will now be equal to H naught plus IH bar by 2m d by dx QA plus IH bar by 2m QA d by dx plus q square a square by 2m. Okay. Now let us evaluate the term. So let me write down again the Hamiltonian. H is equal to H naught plus IH bar by 2m d by dx of q is a constant, so you can take it out, of A plus IH bar by 2m q A d by dx minus plus q square by 2m A square. Okay. Now let us evaluate the term d by dx of A. But when this is Hamiltonian, it has to be always evaluated with respect to some function. Okay, some function psi of x. So this is equal to, okay. Now there are product of, so they will get dA by dx, okay, into psi of x plus A times d by dx of psi of x. Okay. Now this is nothing but del dot A. Okay, plus A, this is nothing but del. Now according to Coulomb gauge, del dot A is equal to 0. So this is nothing but A del, or this is nothing but A d by dx. So your H is equal to H naught plus IH bar q by 2m d by dx of A, that is nothing but A d by dx, A d by dx, and there is another term which is similar to that, it is equal to IH bar q by 2m A d by dx plus q square by 2m A square. So this is nothing but H naught plus these two terms are equal, so 2 times, so this will be IHQ A d by dx plus q square by 2m A square. So this is nothing but H naught plus IH bar q by m, by m A del plus q square by 2m A square. Okay. So your Hamiltonian now comes out to be H equals to H naught plus I h bar q by m a dot del minus or plus q square by 2m a square. Okay. So, that is the Hamiltonian that you are going to get. So, which means your h prime of t should be equal to I h bar q by m a dot del, okay, plus q square by 2m a square. Okay. Now, in spectroscopy the amount of light is very feeble, so that is called weak perturbation. In the weak perturbation limit, okay, we will ignore the a square term. Therefore, h prime of t will be equal to I h bar q by m a dot del. That is your Hamiltonian or the perturbation Hamiltonian. So, your total Hamiltonian nothing but h naught plus h prime t. So, h naught is something that is the molecular Hamiltonian, and your perturbation Hamiltonian, time dependent perturbation, is just given by I h bar q by m a dot del. Okay. Now, we know the, now I can slightly modify this. Now, we know the Hamiltonian, the perturbation Hamiltonian. So, this is nothing but a q by m times minus I h bar del. Okay. What is minus I h bar del? Minus I h bar del is nothing but p. Okay. Remember, minus I h bar d by dx is equal to operator p. So, this is nothing but minus q by m a dot p, that is your h prime of t. Okay. So, this is my time dependent perturbation. Okay. Now, we know what is the time dependent perturbation. Okay. We will stop it here and continue in the next class.